Hello everyone, I'm Harshita Devraj and I'll be talking about the Abelin-Zeithaml method, which is a way to basically calculate the repulsive van der Waals forces between an atom and a conducting body of any shape. So we will briefly discuss the Abelin-Zeithaml method and why this method has an advantage of relating the quantum problem to a classical one in electrostatics in a systematic way. So this is mainly when the corresponding classical problem admits a simple solution by the image method. So in order to compute the van der Waals interaction between two neutral but polarizable atoms, like let's say for example an hydrogen atom, we first need to find out the interaction Hamiltonian operator between them that should be used in the perturbative quantum mechanical calculation of their interaction. So in this case, the unperturbed Hamiltonian operator of the system is formed by the two atoms will simply be the sum of the Hamiltonian operators of both the atoms separately. So this will already include the Coulomb interactions existing in both the atoms. So we are considering this case to be in the short distance regime, that is the non-retarded regime. So because we are in the short distance regime, this is achieved by computing the Coulomb interaction between all charges of one atom and all charges of the other atom. So once the distance between the two atoms is small enough to make these retardation effects negligible, but is still much greater than the Bohr's radius, we can do a Taylor series expansion. So what we'll do is a Taylor series expansion will be performed, and this will lead to the dipole-dipole interaction term coming out as the dominant term. But if you were to take the case of a neutral but a polarizable atom, and it is interacting with a macroscopic body, and it is perfectly conducting, let's say, we'll have to take into account such a huge number of pairwise Coulomb interactions. So in such a case, it will be convenient for us to introduce a term called the electrostatic potential phi, and we can write the Coulomb interaction Hamiltonian between the atom and the conducting body in terms of an electrostatic potential. So U Coulomb is equal to half of rho into phi and integrated over the volume. So the electrostatic potential satisfies the Poisson equation and is subject to a boundary condition on the surfaces. So what we're going to do is we are going to ground this perfectly conducting body, and so this will mean that the boundary condition will become that the potential at the boundary is 0. Now solutions to the Poisson equation can be obtained from the Green function method. So in Green's function we have this equation del square G is equal to minus dou of R minus R dash, and we'll put this and find the potential. So phi is equal to 1 by epsilon naught G into rho, again over the volume. So a general solution for the potential can be written as this expression. So in order that the electrostatic potential obeys the boundary condition, we also will need to apply the same boundary condition, that is at the surface the potential is 0. So the Green's function also has to be 0. So we'll have to impose that condition. So in terms of the Green's function, the energy function takes the term of 1 by 2 epsilon naught rho of r into G into rho of r dash. So since the Green's function is nothing but the Poisson equation for a point charge, we can easily find that the Green's function is 1 by 4 pi r minus r dash whole mod. So this solution, however, does not obey the boundary condition that we imposed. So to make it such that it will adjust to this boundary condition, we will add another solution, another term GH to this solution, that is to the homogeneous equation, and where GH should satisfy the Laplace equation. So del square GH is equal to 0. So all the information of the geometry of the system will be contained in this GH term. So the desired interaction Hamiltonian operator between the atom and the grounded conducting surface is given by this expression, which when we simplify, we get the below equation. So the atomic dipole moment that appears is a quantum operator. So in the first order perturbation theory, it gives rise to the desired non-retarded interaction energy between the atom and the conducting surface. So this we're going to denote by U and R. This U and R is proportional to the quantum expectation value. So U and R is proportional to the quantum expectation value, which we're going to give by this equation. But we have to keep in mind that we always work with an orthonormal basis, meaning we can put this expectation value of dm dn operators, we can write it in the form of dou of mn expression value of d square m, because we only work with an orthonormal basis. So if we insert this expression into u of n r, we get this equation, a simplified equation, where this n term is replaced by m because of this dou. So we can, this equation is the expression obtained by Eberlein and Zettel. This method has advantage because it relates the quantum problem to a classical problem in electrostatics, and it takes advantage of that, and it's very simple. Like, it's basically saying that to obtain the non-retarded van der Waals equation energy of an atom near any conducting surface, one just needs a homogeneous solution of the Laplace's equation GH corresponding to that particular geometry. So that is all we need. And indeed, denoting by the electrostatic potential of that configuration, we can depose the sum of the potential of a charge plus the potential of the image charges. So we'll donate the image charge potential by phi I. Since the potential of the single charge satisfies Poisson equation phi I, this also obey the Laplace equation. So together with the boundary conditions that have been imposed, we have two equations. So del square phi I of r is equal to 0, and this is the boundary condition that at the surface it has to be 0. So when we put these two equations, we can now directly get the Green's function, that is the GH, the function GH, not the Green's function, GH, that corresponds to this solution. So we get GH to be epsilon naught phi I of r divided by q.
Okay, so now I will start from the introductory examples. In this section, we apply Eberlein's and Zettel's method we just discussed in these introductory examples, which are namely for an atom which is close to a grounded conducting plane and an atom which is close to a grounded conducting sphere, where the image method which can be applied with no difficulty. In the later cases, it is possible to solve for a now non-grounded isolated sphere as well. However, in that case, we require appropriate modifications of the method which we have outlined in the previous sections. Since GHR of R dash no longer satisfies the boundary conditions. So I will explain the first example, which is atom close to a grounded conducting plane. This is the diagram for that. So for this, we will imagine a polarizable atom which is positioned at R naught near an infinite conducting plane which is located at Z is equal to 0, which we can see here. And this scenario is serving as the backdrop of our investigation into the interaction energy dynamics, which we are going to find here. So the main objective of our this example is that we are going to employ the image charge technique by introducing an image charge Qi, which is going to be minus Q, symmetrically positioned relative to the original atom across the conducting plane. So this technique facilitates the analysis of the electrostatic potential. With that thing, we're going to find electrostatic potential. So the electrostatic potential phi I of r, which created at r, which is created by the image charge minus q, which is located at the position r I dash, is, as we can see, it's very easy to know, and it is phi of I r is equal to minus q divided by 4 pi epsilon naught into r minus ri dash, where ri dash is equal to r dash minus 2z dash z cap. So hence from the equation 18, and we are going to find the GH function with this equation. And because we have found this, the GH function we are going to find is as here, which is easy to find, which is pi I of r divided by q epsilon naught, which we will solve, which is very easy to do. We'll get minus q by 4 pi r minus ri dash. Now we are gonna apply the Eberlein and Zettel method. So we will incorporate the function we just found, GH function, into the Eberlein and Zettel method, which allows us to compute the interaction energy UAP at R naught. So we will now properly delve into the practical application of Eberlein and Zettel method to compute the interaction energy, as I said, between the atom and a grounded conducting plane in our case. To begin, we'll take the derived function g function into the methods framework, and we will do it. So as we all know, this is the GH equation here we can see it. So we will substitute this expression, this, and we will get this equation. The bigger equation we have written here, UAP at R naught is equal to minus 1, 8 pi epsilon naught summation, and all these things at R is equal to R dash is equal to R naught. So this is the final equation we have from which we're going to find the interaction energy. So here we will now try to find the derivatives in the previous equation, this equation, and that can be very easily computed. Like for instance, for the first coordinate, if we take m is equal to x, we are gonna get, like here we have solved it, we are gonna get 1 by 8 z naught of cube. Z naught cube. This is the equation we'll get. The same result will be valid for y, which will be dy dash. This thing is equal to 1 by 8 z0 z naught cube. But when we take m is equal to z, we will get the following result, dz z dash, and this is equal to 1 by 4 z naught cube. So we are gonna put these derivatives which we get into the equation we have above, and we are gonna get our result as UAP Z naught, which is equal to this interaction energy, the final energy. And this is a well-known interaction energy between an atom and an infinite conducting plane in the non-retarded regime, which was firstly obtained in 1932 by Leonard Jones. So this derived expression, it represents the interaction energy between atom and the grounded conducting plane. It accounts for the contribution from the polarizability along different axes and the distance from the infinite plane. The negative sign here indicates that this is an attractive interaction. So by analyzing the interaction energy, we gain insights into the nature and strength of the interaction in the non-retarded regime. Understanding such interactions is very crucial for various scientific endeavors ranging from material science to quantum mechanics. In summary, all this means that the application of Eberlein and Zettel method coupled with the provided equations we have like GH and the image charge method, it allows us to quantitatively analyze the interaction energy between an atom and a grounded conducting plane, which provides valuable insights into the fundamental physical phenomena. This is my part. The next example is going to be explained by Simranjit. Thank you.
Simranjit Kaur. In this section, we investigate the interaction between an atom and a grounded conducting sphere. This scenario presents an electrostatic problem with practical applications in physics and engineering. So, imagine an atom situated near a grounded conducting sphere. The atom serves as a point charge q positioned at r dash in the presence of conducting sphere. To address this electrostatic problem, we turn to the image method, a powerful technique commonly employed in such scenarios as described in Griffiths. So, let's begin by setting up the problem. An atom is placed in the vicinity of a grounded conducting sphere with radius r and center c. We analyze the electrostatics of this problem by considering a point charge q located at position r dash, at x dash, y dash and z dash in the presence of conducting sphere. The image method for this problem tells us that we have to put an image charge qi positioned at r dash I, which is seen in the figure 1. Hence, the potential created by the image charge at a generic point r, which is greater than r, is given by this equation. Now, substituting the image potential into our previous equations, we derive the homogeneous solution for this configuration. GH r dash is equals to minus r divided by 4 pi r dash r minus ri dash. On towards Berlin-Zettel formula. Now let's apply the formula. Considering an isotropic atom, we simplify analysis by assuming dx square is equals to dy square is equals to dz square is equals to d square by 3. With no loss of generality, we orient the axis so that the atom is located at r naught. So after these whole calculations, we proceed to compute the expression, which is equation 28. Also, the equation 24, this equation describes the potential phi I created by an image charge qi at position ri dash in the presence of a grounded conducting sphere. It incorporates the image charge technique where an image qi is introduced to mimic the behavior of original charge q in the presence of conducting sphere. And this Green's function, this equation represents the homogeneous solution for the configuration of the atom near the grounded sphere. It describes the Green's function, which is a fundamental solution to the corresponding partial differential equation in electrostatics. And we were at equation number 28, which describes a partial derivative involving the coordinates x dash and x with respect to a particular expression. It is evaluated at a specific point r equal to r dash, which is equals to 0, 0, z naught. This result is crucial for further analysis of the atom-sphere interaction. So, an identical result is obtained for the coordinate m is equals to y. In the case m is equals to z, it can be shown with an analogous but linear calculation, that dz dash dz r minus r I dash by R inverse at R is equals to R dash. This gives the equation 29. And collecting the previous results and substituting them into the equation 16, we finally obtain the dispersion van der Waals interaction energy between an atom and a grounded conducting sphere as U is equals to this expression at Z0 and R. And for later convenience, we rewrite equation 30 in terms of R and the distance between an atom and the sphere Z0 minus R, which we denote by A. So substituting A, which is equals to Z0 minus R in the equation 30, we get this equation 31, which states UAGS is equals to D square by 24 pi epsilon naught A cube into this whole expression. So the equation 31, this represents the potential energy of the atom near the grounded sphere. It is derived based on the interactions between the atom and the conducting sphere. The term involving D square represents the average of the squared transition dipole moment of the atom, while A represents the distance between the atom and the grounded sphere. So for an atom with a dominant transition frequency, we can write the equation 31 in terms of its static polarizability alpha, recalling that for an atom in its ground state, which is equals to alpha is equals to 2 by 3 H cross, where summation is equals to d n naught whole square by omega n naught, where omega n naught is the transition frequency between nth state and the ground state, and d n naught is the corresponding transitional dipole moment we have for an atom with a dominant transition, say between the fundamental state and the first excited one. So the final equation reduces to this, which represents an alternative expression for the potential energy in terms of static polarizability alpha of the atom. It relates the potential energy to the transition frequency and the transition dipole moment of the atom. So each equation contributes to our understanding of interaction between atom and the grounded sphere, incorporating concepts from electrostatics, quantum mechanics, and mathematical techniques. So the previous results were obtained for the first time by Teddy and collaborator. However, the agreement of our equation 34 and their result is off by a factor of 3. But a discrepancy by a number factor between the two results is expected because those authors employed fluctuating dipole methods, which is not expected to provide the correct numerical factors, though it does give the correct behavior of the interaction. The atom sphere system has been discussed by many authors for spheres with different properties and for regimes other than the non-retarded one, and recently has been a subject of great interest. In fact, the result expressed in equation 31 was also obtained by Buman as a particular case of a more general discussion, and the equation 34 is valid for any values of R and A, provides that the conditions for the non-retarded regime remain valid. In the limit R tends to 0, we get the final equation, which is this one, which reproduces the non-retarded result of the atom plane system. At last, we considered an atom located near a grounded conducting sphere with the radius r and c. So the atom acts as a point charge q positioned at r dash in the vicinity of a conducting sphere. So we applied the image method, which is a commonly used technique in such scenarios. The image method involves introducing an image charge qi strategically positioned to mimic the behavior of the original charge in presence of conducting sphere. So in this case, the image charge qi is placed at the specific location ri dash, which is determined based on the geometry of the problem. So talking about the potential calculation, with the image charge in place, we calculate the potential created by image charge at the generic point R. The potential, denoted as phi, provides valuable insight into the electrostatic interaction between the atom and the conducting sphere. So the presence of a grounded conducting sphere significantly affects the electrostatics of the atom situated nearby. By employing the image method, we can effectively analyze and characterize this interaction, enabling a deeper understanding of fundamental principles of electrostatics. Furthermore, this analysis facilitates practical applications in various scientific disciplines, including physics, engineering, and mathematical science. In this scenario, the grounded conducting sphere acts as a boundary condition that influences the behavior of the electric field surrounding the atom. The image charge placed using the image method helps simplify the analysis by effectively incorporating the effect of conducting sphere into electrostatic calculations. By considering the potential created by the image charge, we gain valuable insights in how the presence of conducting sphere alters the electrostatic interaction between the atom and its surroundings. This analysis not only deepens our understanding of fundamental concepts, but also has practical applications in electrostatics and quantum mechanics also. In summary, by studying the interaction between an atom and a grounded conducting sphere, we gain valuable insights into the complex interplay between electric charges and boundaries, contributing to our broader understanding of electrostatics and its applications.
So I will be discussing about another practical example that uses the image method for the calculation of van der Waals force between like an atom and a conducting surface. So the example I'll be using uses the Berlin-Ziegler method, and this example is of an atom close to an isolated conducting sphere. So this case differs from like the previous case of the grounded conducting sphere because it does not satisfy the boundary condition as given, like the Green's equation. It does not satisfy it because the sphere is not grounded. Like if it has any charge, it will have a potential. Therefore, it will not satisfy the boundary condition. So about the Berlin-Ziegler method, it is used to calculate the electrostatic potential and field around conductors in the presence of external charges. This method is particularly useful for solving problems involving conductors that are not necessarily grounded. Like this problem is a problem where we can use the Berlin-Ziegler method. But one of the key aspect of Berlin-Ziegler method is like it uses like the previous image charge aspect itself. It uses like the concept of image charges to simplify the problem. So in the image charges, we place symmetrically a fixed charge at the origin, and with respect to that, we solve the problem. And we use the Berlin-Ziegler method. Like the one advantage is that we do not have to like it respects all boundary conditions. Like if there is external fields or potentials, it can be used for all that, and it's even applicable for isolated conductor, like in this case where the boundary condition will not be satisfied. So here like since the sphere is not grounded, we like if it has any charge, if like the presence of any charge will like it causes like a potential in the sphere.
And like in the before, like the equation 6 to like 8 to 16 in the formulation of Eberlein-Zittel method, like they do not depend on like the boundary condition, and hence is still valid in this case. And it coincides with the electrostatic potential created by the image charges. Like let's take an isolated sphere of radius r, and we take a charge q at a position r dash. So there will be like an extra image charge located at the origin, whose electric charge will be equal to r, like the radius, by r dash into q. Like, and we take this extra charge into account, and we like formulate the corresponding functions. So here the Green's function, including these charges, will be as the following. And here Ri dash will be equal to r square divided by r dash square into r dash. And for applying the Eberlein-Zittel formula, we first we will compute the relationships with the partial fractions. Once we have gotten this, we will use the expression from the above case, that is like the potential energy of the ground sphere, and with that we will get like the potential energy of the isolated sphere, like atom potential energy between the atom and the isolated conducting sphere. So we can see, like from the previous case, this is the r divided by z0 raised to 4 is our extra term. And like for easier understanding, we can substitute like with the following relation, that is a is equal to z0 minus r. And like mathematically we can say that the second term is greater in magnitude than the third term. This third term is the one that comes due to the isolated conducting sphere. Because of that, we can say the force would be attracted, but it would be less in magnitude, because like the grounded sphere, it can have it can change like the charge acquired, and hence it will always have like a higher, it will always be more the force will always be more attractive. And finally we'll take like the limit of r tends to 0 as like the atom approaches, and we have done this approximation with alpha s, and we will get like the following result as like the atom approaches the sphere. The potential energy will be as follows. So in the last step, we have assumed that the transition from the fundamental state to the first excited state is dominant. So this results in a London-like dipole-dipole interaction as expected. So that is for the atom, that is that is for the atom which interacts with the isolated conducting sphere. So the next part will be taken by Kanika.
Hello, my name is Kanika Banjare, and I'm gonna talk about topic 4. So, atom close to a conducting Gauss head surface. So, in section 3, we address simple case involving an atom in proximity to conducting surface. But now we'll move to more complex scenario. The interaction of atom with conducting surface shaped like a boss head. This surface is comprised of conducting hemisphere with radius r, accompanied by an infinite conducting plane. So this configuration is also called hemispherical boss. So to analyze this setup effectively, we'll utilize the concept of image charge. So, three image charge are required in this case. You can see that this is the boss head. So three image charge are required in this case. To see this, consider a charge Q at position R. You can see here is the Q. In the presence of the conducting boss head, will introduce this is a QI1, which is introduced here, and its position is RI1. So in cylindrical coordinate, R dash equals to under root of uh, rho square, rho dash square plus z dash square, which lead to the position to the charge qi1 equals r upon under root of rho dash square plus z dash square multiplied by q. So in the atom sphere case, a pair of q and qi1 is initially introduced to provide null potential. But however, this configuration fails to satisfy the desired boundary condition. To address this problem, two additional charges were introduced, which were the image charge of Q and QI1. With the inclusion of these two image charges, minus QI1 and minus Q, the potential on the plane z equals to 0 becomes null, while still maintaining the potential on the boss head, still maintaining the null potential on the boss head conducting surface. The position of the four charges are given here: R dash, R dash I1, R1, R dash I2, R dash I3. So with the image configuration, the potential generated by this image charges is just a superposition of uh, potential charges created individually. So will be become the sum of the potential created by qi1, qi2 and qi3, namely phi I equals to this. Then we have this psi, this using this previous expression of qi1, qi2, qi3, as well as r dash I1, r dash I2, r dash I3, will define qi is psi minus, psi plus, and psi. So the function gh r dash for the boss head can be written like this, where xi r and r dash is written like this, and xi plus minus has become like this. So we have now used the equation 1, which I've used previously, and the dispersion interaction energy of the boss head conductor with the atom at a generic position, like rho naught, phi naught, and z naught, can be obtained from the equation 6. After a lengthy and straightforward conversation, we define the energy is like this, and ought to be like this, where capital psi rho psi for the phi and psi for the z become like this, and with zeta r naught and z naught is equal to this. So as expected, the interaction energy does not depend on a phi due to the axial symmetry of the system. Furthermore, one can immediately recover the atom plane result 23 by taking r equals to 0. We plot the interaction energy given by equation 49 multiplied by the r cube as the function of z naught upon r for the particular case where atom is on the oz axis, rho equals to 0, and the atomic polarizability is the direction is dominant. So this is the plot. So you can see that it's becoming saturated after some time. It's increasing slowly, then getting saturated after some time. And it's interesting to compare the interaction between the atom and the Bose head with the atom grounded sphere case to analyze the curvature effect. We'll now use the isotropic atom for the consistency in equation 30, comparing them up to the third order. So by the Taylor expansion, we can found that keeping up the third term in z naught minus r upon r, we get the respective expression. And the equation 54 and 55 coincide up with the order in z naught minus r upon r. In other words, up to z naught minus r upon square whole square upon r square, the interaction of the atom with the Bose head surface is same as that of the atom with a sphere. This is a reasonable because the atom very close to a Bose head surface cannot distinguish from the surface, and as as the distance between the atom and the Bose head increases, the difference between the two surfaces become apparent, and the comparison of UAGS and UBH, and the expression is given here, so you can see that. So the conclusion is that the method given by the Abelin and Zettel offer a practical approach to compute van der Waals interaction between an atom and a conducting surface of any shape. And this method have been applied to various scenarios, including the simple scenario and a more complex scenario like above, like atom near and conducting head surface. And the advantage of this method is that it has the ability to quickly transform the problem into classical electrostatic problem, so allowing the established method for solving Laplace or Poisson equation. So other approach such as the green method have been employed for certain scenario. Nevertheless, Elberlin and Zettel method combined with generalized method introduced by the Somerville has proven effective for the intricate geometries. So the dispersion force remain a such subject of active research, especially for the quest for the repulsive force, which is significantly in diverse contexts. Notably, so past studies have explored the repulsive Casimiri poles and interaction between electrically and magnetically polarizable atom. So this was the conclusion. Thank you.